Hi everyone, I am Maheswari, Assistant Professor of Mathematics, St. Joseph's College for Women, Tirupur. We are going to discuss about composition function and inverse function, which is a subtopic of discrete mathematics. Function. First, we are going to see the definition of function. A relation f from a set x to another set y is called function if for every x belongs to capital X, there is a unique y belongs to capital Y such that x comma y belongs to f and it is denoted by f is a function from x to y. If y is equal to f of x, comma, x is called pre-image and y is called image of x under the function f. X is the domain of f and it is denoted by d of f. Y is the range of f and it is denoted by r of f. It means the domain is denoted by d of f and range is denoted by r of f. Types of function. Functions is one-to-one function, on-to function, then bijection function. Bijection means it have both one-to-one and on-to. One-to-one function. A function f is a function from x to y is called one-to-one function if distinct element of x are maps into distinct element of y equivalently. If f of x1 is equal to f of x2 whenever x1 is equal to x2, or if f of x1 is not equal to f of x2 whenever x1 is not equal to x2. Example, the definitions of one-to-one distinct element of x are maps into distinct element of y. First is A and second one is B. A1 are maps into B1, A2 are maps into B2, A3 are maps into B3, A4 are maps into B4. Here the distinct element of A are mapped into distinct element of B. Onto function. A function f is a function from x to y is onto or surjective if the range is called codomain. In other words, a function f is onto if and only if for every y in capital Y there is an element x in capital X such that f of x is equal to y. Here f of x is equal to y is the onto condition. It is not one-to-one function but it is onto function. Example, here the first one is A set, the second one is B set. Here the element of A is A1, A2, A3, A4 and A5. The element of B is B1, B2, B3 and B4. It is onto function but it is not one-to-one function because any two element of A1 are connected same element of B. Bijection function. A function f is a function from x to y is called bijective if it is both one-to-one and onto. It is one-to-one and also onto. The example of bijection function is the first set is A and the second set is B. Every element of A is connected to every element of B. It is called bijection function. Composition function. If f is a function from A to B and g is a function from B to C, then the composition of f and g is a new function. G composition f is a function from A to C denoted by g composition f. Here g composition f of x is equal to g of f of x for every x belongs to capital A. We can write g composition f of x is equal to g of f of x. Example, the first set is A and the second set is B and the third set is C. The mapping of A and B is F. The mapping of B and C is G. The mapping of A and C is G composition F. Property. When f is a function from a to b and g is a function from b to c are functions, then g composition f is a function from a to c is an injective, surjective or bijective according as f and g are injective, surjective and bijection. Proof. Let a1 comma a2 or belongs to capital A. We have to find G composition F. So G composition F of A1 is equal to G composition F of A2. Here G composition F of A1 is written as G of F of A1 is equal to G of F of A2. Next, G of f of a1 is written as b1 is equal to g of b2 because f of a2 is written as b2. Next, g of b1 is equal to g of b2 is written as b1 is equal to b2. Therefore, G composition F is injective. Let C belongs to capital C. There exists B belongs to capital B, comma G of B is equal to C. There exists A belongs to capital A, comma F of A is equal to B. G composition F of A is equal to G of F of A by the statement f of A is equal to B. Here G of B is equal to C because the statement G is a function from B to C. It will come G of B is equal to C. Then G composition F is onto. Next, the problem. Let f of x is equal to x plus 2, g of x equal to x minus 2, h of x equal to 3x for all x belongs to capital R, where capital R is a set of real numbers. We want to find G composition F, F composition G, F composition F, G composition G. First option is G composition F of x is equal to G of F of x equal to G of the statement of F of x is equal to x plus 2, that is here written. G of x is x minus 2. Within the bracket of G is like as x, that will write here x plus 2 minus 2 by G of x is equal to x minus 2. The plus 2 and minus 2 is cancelled, so it will come only x. Therefore, G composition f of x is equal to x, comma x for all x belongs to capital. The second option is F composition G. F composition G of x is equal to F of G of x is equal to F of x minus 2 because in the statement G of x is equal to x minus 2 is equal to x minus 2 plus 2 because f of x is equal to x plus 2 is noted in the statement. Here minus 2 plus 2 are cancelled, will have only x. Therefore, f composition G is equal to x comma x for all x belongs to capital R. The third option is F composition F. F composition F of x is equal to f of x. is equal to f of x plus 2. It means f of x is equal to x plus 2 is equal to x plus 2 because f of x is equal to x plus 2. Within the bracket of f is x plus 2 will we want to add 2. So we have x plus 4. Therefore, f composition f is equal to x comma x plus 4 for all x belongs to capital R. Here the first x is in the equations of left and the second x plus 4 is in the equations of right. The fourth option is G composition G of x is equal to G of x is equal to G of x minus 2. By the statement G of x is equal to x minus 2, after that G of x minus 2, it is again as a form of G of x. We will write x minus 2 is equal to x minus 4. Therefore, G composition G is equal to x comma x minus 4 for all x belongs to capital R. Hence, proved. Next, the definition of identity mapping. The mapping Ix is a function from x to x is called an identity mapping if Ix is equal to x comma x such that x belongs to capital X. Here Ix is a function from x to x is the identity mapping of I. Inverse function. The function f is a function from x to y. The inverse function of f is f bar or f inverse. Then f inverse is a function from y to x is called the inverse function of f. If f is a function from a to b and g is a function from b to a, then the function g is called inverse function of f. G composition f is equal to ia and f composition g is equal to ib. Theorem. Let f is a function from x to y and g is a function from y to x. The function g is equal to f inverse if and only if g composition f is equal to ix and f composition g is equal to iy. Proof. Let us consider if there is any other function than g, that is h is a function from y to x such that h composition f is equal to ix and f composition h is equal to iy, which is equation star, since composition functions are associative. H composition f of g is equal to h composition of f composition g. H composition f is equal to ix composition of g is equal to h composition f composition g is equal to iy. Ix composition g is written as g and h composition iy is written as h. So we get G is equal to H, which is equation number I. By applying equation number 1 in star, we get G composition F is equal to Ix and F composition G is equal to Iy. By the theorem of double star, we get G is equal to F inverse. Hence proved. The theorem double star is written in the right side. If f is a function from x to y is invertible, then f inverse composition f is equal to ix and f composition f inverse is equal to iy. Thank you.